So, we're going to do, everybody got their calculators in front of them.
Oh dear.
We're going to do a little bit of calculating and a little bit of monkeying around here. So we're going to start talking about transmission lines. So up to this point, when I drew stuff on the board, we just drew wires and we kind of ignored what was happening. Now we're going to pay a lot more attention to what's going to happen, okay? So what I've got here is I've got a typical 100-watt amateur radio transceiver. I just showed it as a AC signal source with an internal 50 ohm resistor. That's what our transmitters are. Doesn't really matter if it's a handheld or a desktop. I'm running it off a 13.8 volt station power supply. Very, very typical for what we would run at an HF station. Transmitter efficiency is 50%, which probably a little better than 50% with a modern transceiver, but let's say this is an old one from the 1980s. So first off, if it's a 100-watt transmitter and we only got 50% efficiency and a 13.8 volt power supply, how much current do we have to provide to put out 100 watts? Calculate.
Oh boy.
P is equal to EI. And we're asking for current.
I is equal to P over.
Is it E over P or P over?
3.62 amp.
So.
Okay.
I is blue.
100. 8 amps.
Yeah, but you gotta double this 50%.
That's right, 50% efficiency, you need to double. Somebody said that, right?
Oh.
No, you divide it by half.
You know, you gotta double it.
What do you double
What
on?
do you mean double?
The transmitter is only 50% efficient.
Yeah.
That means
Yeah.
that means half the power you put in is gone.
So you have 100 watts, so there's 50 left,
So
right?
if you want this thing to put out 100 watts, you have to put 200
That's
watts
what
of
you mean,
power
right?
in.
Oh.
Right?
Oh.
So
14.5?
so the magic is what did you say?
14.5?
14.5?
Oh.
Or am I wrong?
Yeah, 14.5 is very close.
16.1 is what I got.
Well, I got 14.49275363.
It's about 14.49 something. So that's what I got. So that was just a reasonably easy Ohm's law calculation. The thing I threw at you was a 50% efficiency, so you had to realize
Yeah.
that since your transmitter is not, if you put 100 watts into a modern transmitter, you don't get 100 watts out. Okay, modern transmitters are probably 75 to 80% efficient. Older ones, 50%. And real old ones, 20% efficient. They took lots of power. So in other words, your 13.8 power supply better be able to deliver about 15 amps or more to safely run your 100-watt HF rig. So, that's just a simple thing that we can do right there. Okay, that being said, we know all about our power supply. That's the DC power supply. Once again, we have a 100-watt transmitter with a 50 ohm resistor going into this piece of coaxial cable. It's RG213 cable, going some distance and going out into an antenna. So what is the current and the voltage at that point at the entry of the feed line?
What line? Sorry.
At this point, right where the feed line connects to the back of our transmitter, what is the current and the voltage on that antenna connector?
Solve for current and solve for voltage.
Yep, you got 100 watts, you got 50 ohms, that's all you need. Right?
Okay.
See which one they solve first, voltage or current. Which one are they going to solve first?
And the voltage.
70 voltage.
I heard the magic number, somebody said
I
it.
didn't say
So,
0.7.
so
Yeah.
I
Okay,
got 7.24 amps. Is that right?
no,
Got 4.47 amps.
no.
Oh.
Well, shouldn't the voltage be
Under,
1.4 amps?
70 volts?
70 volts, isn't that amazing?
Yes, it
We only have a 12 or 13.58 volt power supply, but we still get 70 volts up there.
Yeah,
Isn't the laws of physics amazing?
it's not working.
And that's why you don't stick your fingers on your antenna connector and key up. Even with a 5-watt transmitter, you will get a burn, believe me. Okay, it's amazing how that works.
Okay, so
Oh, how did we get those numbers?
Yes, he lost me completely.
Power equals I squared times R. Right? So I equals square root of P over R, which is the square root of 2, which is 1.414. And if you multiply 1.414 by 70.7, you get 100. Right? Power equals V times I. It's just Ohm's law being reiterated over and over again. Just we're turning it around backwards and plugging in numbers the opposite way, but it all comes back to Ohm's law. Makes sense? All the numbers add up, everything matches. Okay? So if our antenna here is a 50 ohm match,
So, question. So, which P is that there in I?
100 watts.
That one. So it's 100 divided by 50,
yep,
which is 2.
Root 2
The
is
square of 2.
square root of 2 is 1.414 last time I checked.
Yeah.
It's actually it's more digits than that, but it's one of those numbers that goes on forever. It's 1.414 blah 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 blah.
That's a
Yeah, but we have a little rounding error, close enough. But if you multiply those two numbers together, you imagine you come back with 100 watts is what we're putting into the wire. So we're pulling 200 watts from our power supply to do it, but we're interested in what's on the wire, not down here anymore. So that goes across voltage of 70.7 volts, right? So over here, assuming we have no loss in our feed line, does the math work out? Ignoring this now, so if we got 70.7 volts and 1.41 amps and 50 ohms, is that all, does the numbers go around in the circle? It all comes out to 100 watts. So we're going to radiate that 100 watts out into the ether, and people are going to hear us for miles around. We hope.
You ready?
Okay. So, what happens when a bird lands on the antenna? Or an ice storm or snowstorm like this morning happened, and your antenna gets coated with a thick layer of ice, and now it's 25 ohms.
No, it should be half then, right?
What do you mean half? Well, if we got, P equals what?
E squared R.
I squared R. So P equals, well, I is that. So 2, square that, you come up with 2 times R. So P equals 50. But hang on, we put 100 into it. We're only getting 50 out. Where's the other 50?
And birds.
The ice.
yes, in the bird.
Heat.
No, everything's lossless. There is no heat loss.
No.
Well,
It's
a
getting
miss.
reflected back.
It's getting reflected back. So 50 watts of our power is still going into the load. 50 watts comes back the other way, and when it sees this 50 ohm resistor, that will dissipate it as heat, and we'll be happy. So we get a 2-to-1 standing wave ratio, 2-to-1 simply because we divided that load by 2. We could have went to 100 ohms and still got a 2-to-1. And now our transmitter is getting warm, because now this 50 watt here that's designed to dissipate 100 watts now has to dissipate the 100 watts that we're transmitting plus the 50 watts that's coming back. So really this poor little resistor inside our transmitter is now dissipating 150 watts of power. So our transmitter is starting to get hot. And if it's a modern transmitter, it'll have temperature sensors and SWR sensors, and it'll automatically turn its power down to avoid it from burning itself up. If it's a Chinese-made one, good luck. Hopefully you've got big cooling fans and bags of ice. Okay. So, by matching the impedance, so if we have 50 ohms there and 50 ohms there, we get what we call maximum power transfer, and all is happy. And that's the ideal situation. But as soon as we have a mismatch where it's not 50 ohms on the far end, we get reflected power. And so the power goes forward, it hits that antenna, some gets dissipated, but some gets reflected back. The stuff that gets reflected back gets absorbed, because remember 50 ohms is what it's looking for. It gets absorbed perfectly in the transmitter. 50 ohm in the transmitter, of course, dissipates that as heat and starts getting hotter and hotter and hotter. And even guys, if you've transmitted with your handheld radios on high power for any length of time, you can actually feel the body of the radio starting to heat up. That's because these rubber duck antennas they're basically not even an antenna, they're a piece of rubber. So, you know, the majority of your power is being reflected back into the radio. And even at running low power, 3 watts or 5 watts, it doesn't take long because your radio now has to dissipate the power that it's putting out plus the power reflecting back, which is a lot in the case of a handheld. The antennas are very poor, so.
Is this considered a rubber duck antenna?
Yeah.
It still is.
Oh yeah. So, unless you can specifically tune it, good luck. So the antenna impedance can go above or below 50 ohms and give you reflected things. And there is a way mathematically to tell which way it's going. Little antenna analyzers can do that internally. They can say it's higher or lower impedance and stuff. But that's what happens. And so when that happens, and how fast does this happen? Well, it happens bloody fast. Okay, I mean, these waves are traveling at the speed of light until they hit inside this cable, then they slow down. Anybody know how much it slows down in RG213? It slows down to 0.66 times the speed of light. So about 2/3 the speed of light. That's still bloody fast, by the way. But it does slow down, okay? And it slows down because the speed of light, that 300,000 meters per second or whatever that number, that is in a vacuum or in space. Now, air isn't that much different than a vacuum because molecules are quite sparse in air and it barely slows the RF down at all. So we can call that number, that C in air, is fine. That 300,000 meters per kilometers per second or whatever it is. But as soon as we change out the medium that the RF is traveling through, in the case of RG213, it's a polyethylene plastic. It's like garbage bags, that kind of plastic. The RF travels slower through it because now there's some solid matter to go through. There's some molecules in the way and it actually slows down. So it is 0.66, 66%. That's still bloody fast, but it's a lot slower than the speed of light. Okay. So this thing of the wave coming down here, reflecting and coming back happens, faster than we can blink our eyes. It happens very, very quickly. And so what happens is you get a constant stream of waves coming that way and a constant stream of waves reflecting back. And along the feed line, the waves will add when they meet, crest to crest, and they'll subtract when they meet crest to valley, and you'll end up with what they call a standing wave pattern, or an SWR. And then the standing wave ratio is just that. We can measure the wave the amplitude of the waves going this way versus the amplitude of the waves coming that way, and we just get a number. The proper name is voltage standing wave ratio, VSWR, and all we do is we measure the peak of the voltage of the waves going that way, and we measure the peak of the voltage of the waves coming this way, and we compare those two peak voltages. And that's what an SWR meter does. All it does is it looks at waves going one way, waves going the other way, and they do it just by a diode and flipping the polarity of the diode. The diode will detect them going one way, flip the diode around, detects going the other way, and you look at the ratio between those, and off you go. So, with all these numbers being said, and velocity factor of RG213 being 0.66, hint hint,
It is on the test.
it is on the test.
It
yeah.
seems to be one of their favorite ones.
Yeah. Well, the RG213, the polyethylene coax, that's by far the most common. RG213, RG58 has polyethylene 0.66. There's low loss coaxes out now, like for example the LMR 400s and stuff like that. And really what they do for low loss is for the dielectric, that's the spacer between the center conductor and the shield. If you can make that a vacuum, you have very little loss, because once again, there's no molecules to get in the way. So what they do is they start using plastic materials, but they use a foam material, so they put air bubbles in it. So it's got a lot more air in it and a lot less plastic in it. And because it's got more air and less plastic, the velocity factors will come up to about the 0.8, 0.82, 0.85. And when you get up into the large hard lines that are actually air dielectric, their velocity factors are like 0.98 or something. They're real high. But real popular is like RG58, RG213 that we use in amateur radio, 0.66. So, and all that velocity factor is just a number. It compares the speed of the RF through this cable as opposed to the speed of the RF in air or in a vacuum. So it does go slower, which could be useful. It means you can slow things down if you want to. Okay, so what I'm going to do here is, well, we don't really need all these formulas and numbers anymore, but I'll leave a bunch of stuff up here. What we're going to do is we're going to go like that. I'm going to leave, I forgot to connect my antenna, so I'm going to leave the end of this coax open circuit. Okay, and I'm going to send my RF wave down there, transmit if you will.
You need to put a bucket on the end of that cable to catch the voltage drop.
So if this is an open circuit at the end, and I'm just going to write OC, open circuit. In other words, we just left the cable, end of the cable open, the connector is maybe laying there on the ground or hanging in the air, nothing's connected to it. Okay, and I'm going to use two different colors. I'm going to use blue is going to be current, and red is going to be voltage. So there you go. It's not intravenous, it's current and voltage. Okay, so at the end of this coax cable, once our transmitter starts transmitting, this is an open circuit. So let's talk about the voltage. Do you think the voltage is going to be high or low at that point? At an open circuit.
Depending how long the coax is.
Doesn't matter how long it is.
Zero.
So
You've got infinite resistance.
you've got a very high resistance, which means the voltage will be,
Zero.
so voltage will be high. At the end, we're talking right at the very end of the cable here. Okay. Oh, these colors. Let's try and do this right. So right at the end of the cable, we're going to come down here. So this is the end of the cable on our line, and this is going to transmitter. So we're going to go physically back towards the transmitter, but we're going to start at the end of the line. So at the end of the line, we said the voltage is going to be high. It's going to be, there, something like that. Okay? And as we go back, the voltage is going to do this. And so on and so forth back towards the transmitter. Okay? What's the current going to do? That's an open circuit. The current, if there is any current, it's going to be the leakage across that piece of plastic between the center pin and the outer conductor. It's going to be virtually zero current. So the current is going to go, see if I can do this right, and back towards the transmitter. Okay, so let's just do a thought experiment. So at the end of an open circuit of coax, our voltage is going to be high because basically it's infinite resistance, but our current is going to be zero, no current flow. If we go back towards the transmitter, is that right? Yeah. What's that distance? Anybody? Quarter of a wavelength. What's happened now? Did I draw that right? I probably didn't draw it right.
Well, you have an output to that.
I drew this completely wrong. I apologize.
You did.
My artistry is just so bad that... Okay, let me try and do this right. Something like that, I don't know. A quarter of a wave back, what's happened now is the current was zero, the current is now at a peak. The voltage is at a peak, the voltage is now at zero. So what we've done is we've completely reversed our open circuit, turned it into a short. All we did was move back a quarter of a wavelength. I didn't specify what frequency, just a quarter of a wavelength. We've turned an open into a short. If we go back another quarter wavelength, it's going to be back to an open. It'll flip again. If we go back another quarter, it'll go back to a short. So basically, if we go an odd quarter of a wavelength, so 1 quarter, 3 quarters, 5 quarters, 7 quarters, 9 quarters back, all the way, that open becomes a short. Isn't that cool? We completely flip the impedance. And as we go along the line here, the impedance changes everywhere we go. So we know it's open circuit there, we know it's short circuit there. It's open circuit there, it's short circuit there. But in between those two, it's going everywhere from 0 right up to infinity. So depending where you pick along the transmission line, it'll actually look like a different impedance. Okay, this is called the complex impedance of a transmission line. It's a fun thing to understand. Some people, as I mentioned earlier, kind of intuitively get it, and other people just go, well, that's beyond me. But if you can remember, a quarter of a wavelength will reverse what's happening on a transmission line. We haven't said at what frequency. It doesn't matter what frequency. It's a quarter of a wavelength. Will reverse what's going on. So why in the hell would you ever want to do that? Why? Well, a number of reasons. I have a demonstration. Would you care to inspect that cable? See if there's anything funny about it? Just looks like a piece of coax, I hope.
Yep, that's all it is.
Okay, so I have a piece of RG58 with a BNC connector on it, and it's open circuit on that end, right? You hear what I'm listening to? So I'm going to take the antenna off. This is just a BNC T connector. So I'm going to put a T connector on, and I'm going to put the antenna back on. And hopefully... This happens to be a quarter wave of RG58 at 162.4 megahertz. I measured it this morning in my easy chair. So what the hell did I just do? I took an open circuit, because that cable is open. I just cut it off. I didn't short the conductors. And a quarter wavelength away, that open circuit becomes a short circuit. So for 162.4, when I plug this cable in, it's seeing a short circuit. It's gone. Could that be handy? If you have a powerful transmitter nearby that's constantly interfering with the front end of your radio, could this be a handy thing? And my radio will work fine as long as I stay away from 162.4. I can transmit, I can receive just fine, but when I get to 162.4, it's a short circuit. Or 162.4 times 3. 162.4 times 5, remember? This is a quarter wavelength. Well, at some higher frequency, this is going to be a 3/4 wavelength. And at some higher frequency, it's going to be 5/4 wavelength, and so on and so forth. So very, very handy if you're getting intermod, especially in your base station at home, and every time you hear intermod, you hear the Weather Channel. Well, you know that one of the frequencies that's giving you a problem is 162.4. So you can prepare one of these, which cost all of $2, because this is a cheap Chinese connector. No, I think the heat shrink tubing was worth more than the connector. So that's a way that we can just completely eliminate a station. And there's nothing to say that I can't hook up 2 T connectors, 5 T connectors, 8 T connectors, and take out a whole series of frequencies if I want to. Okay? So this was an example of just taking one frequency out. And all I've done is I've taken an open circuit, used the T connector, and found the frequency I want, and went snip, 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 snip until it's gone. Cutting a quarter wavelength like this is so much fun. You cut 1 millimeter off and throw it away and get a new cable.
Oh, it's very picky, is it?
Oh, get the cable stretcher out, yeah. Okay. It's really handy for that, for eliminating an unwanted station. And that unwanted station could be many tens or megahertz away from you, a long ways away from you. But if, for example, you're hearing intermod products on your home station, and you always hear one particular frequency or one voice channel in that, if you can figure out what frequency that is and eliminate that, chances are you'll eliminate maybe not all of your intermod, but a vast majority of it. So, and yes, I know you have to leave. Go ahead. Sorry. No problem. So that's one useful thing. Another useful thing is, instead of leaving it an open circuit, make it a short circuit. Okay? And stick the T connector at the bottom of your antenna on top of your tower. Hopefully your tower is adequately grounded, like most tower installations should be. Put your T connector in the bottom of the antenna and put a shorted stub on. And what that gives you is it gives you a DC ground. Remember, at DC, a shorted piece of coax cable is it's a short circuit, it's a wire. So now you have DC grounded your antenna, which means lightning, induction spikes, static electricity from the wind, all that kind of stuff will just simply be bled off the ground, but the RF side of it will just squirt on through and not even see that short circuit there. So having a shorted quarter wave stub on an antenna is a very common thing. And all of our repeater antennas, the commercial ones and stuff, if you actually slice the pipes open and look inside there, you will see a quarter wave piece of shorted coax. And the reason to do that is to make the whole antenna a DC ground. Once again, at RF, it doesn't even see that because the short quarter wave away becomes an open. So it's an open circuit. Isn't that cool? So if you need to remember one thing is quarter wave, or an odd multiple of quarter, so 1/4, 3/4, 5/4, 7/4, so on and so forth, simply inverts the impedance completely. So if it's open, it'll invert it to a short, or vice versa. Isn't that just the coolest thing? Did I mention the RF travels on the outer skin of the conductors?
Yep.
Okay, well it does. The RF itself travels just on the very outer layer of these conductors, and lower loss feed lines just simply have a greater surface area. So it's not how thick those conductors are, it's the surface area. Okay, and some of you guys were at the 50 kilowatt transmitter site, and I don't know if you've seen some of the hard line, the real hard line sitting there, which is basically a copper pipe inside a copper pipe to make coax cable, because really coax cable, that's what it is. It's kind of a pipe in a pipe. But you notice the center conductor is just looks like a 3/4 inch copper pipe. Yeah. And once again, it's not the thickness of the copper, it's the surface area that conducts all the power. And in that case, that stuff is rated for 150 kilowatts. Continuous all day long. And because it has such a large surface area. So the core of those things are just, well, it was air. You don't really need anything because the RF doesn't travel through the core of the wires. Now at lower frequencies like the 60 hertz distribution lines in here, pretty much all of the wire is used as a conductor at lower frequencies. But once we get to RF roughly 1 megahertz and higher, the RF actually only travels on the outer skin of the conductor. So.
And there is several questions about skin effect.
Yep, and that's what the skin effect is. The skin effect basically means that the actual RF currents and voltages, I guess, if you will, travel on the outside layer or the outside skin of the conductor rather than through the entire cross section of the conductor.
So in that hard line, was that under the ground in a sealed conduit as such?
No, they don't seal it. What they do is, since it's hollow, they put a bicycle Schrader valve on it and they pressurize it.
No, but the outer one was just pure copper, right?
Yeah,
The
yeah.
shield.
It's just a copper pipe and a copper pipe. It's
So
coax.
and so it was sitting in the ground, so it was
Yep.
okay because that was
Oh, yeah.
the shield as such.
Yeah, yeah.
Okay.
Well, what about this bicycle thing? What was it?
Well, what they do with the large hollow feed lines like that is no matter how well you try and seal them, you can never get a perfect seal. So you're always going to get contaminants from the atmosphere and or maybe water in them if they're running outdoors or underground. So what they do is they pressurize the inside of them, and all they use is dry air. They have a super dehydrator that dehydrates the air down to like almost 0% humidity. It's very, very low humidity. And they pressurize the line, and it's not much pressure. PSI wise, it's like 4 to 6 PSI. It's just enough pressure that if any contaminants or water are trying to get in, it just pushes them out. And so there's a dehydrator compressor that sits there, and it just maintains a constant pressure in the line at about 4 to 6 PSI. And it's a very important thing because if you lose that pressure, nasty things can happen. So you can burn up a $750,000 transmitter in a matter of minutes with a line leak. So there's alarms that tie in. If the pressure goes too low, it rings the engineer's phone and he runs out there and fixes it. So, and just a word on that, I always thought, oh, it's just a dehumidifier, no problem, just dry out the air. But then you think about our Edmonton winter times. When you go from a warm building like this to, say, a minus 25 or a minus 30 outside, the humidity in here may only be 20%, but your glasses still will fog up, right? So when I say dehumidify the air, it's not going down to 20%, it's going down to like less than 2%, because where the transmitter is nice room temperature, toasty, you've been in the building, the outside might be minus 30. So that air is going from room temperature down to minus 30, and you want zero condensation inside those lines. You don't want a single drop of water in there, believe me. So the dehydrator is really dehydrating it like crazy and pressurizing it. So
Did they use nitrogen or?
some do use dry nitrogen, but most, because nitrogen is a pain in the ass, you have to change the bottles and blah, 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 blah. Most just buy an automatic dehydrator. They're expensive. It's $20,000 for that dehydrator. But you plug it in, it sits there and dehydrates for 20 years. I mean, there's not much. The desiccant inside automatically rotates and dries itself out once it reaches a certain humidity level. It's all automated, so. Okay, explain the RF skin effect. The skin effect is explained on page 14-5. We'll jump around a little bit, but 14-5 somewhere they talk about. Oh, at the very bottom of 14-5, it's about the third sentence from the bottom, it says, Remember that due to the skin effect, the RF energy only flows on the surface of the conductor. It does not penetrate like DC and small diameter wire. Yeah, so. And they even tell you that at 10 megahertz, about 0.02 millimeter of the surface is used. At 100 megahertz, drops to 0.01 millimeter. So we're talking very thin layer of the outer conductor is used. And that's why if you buy some of this low-loss coax for VHF and UHF, the center conductor is actually aluminum or aluminium, depending on where you're born, coated with a very, very thin coating of copper. It's cheaper to make because aluminum is quarter the price of copper. And once again, because of the RF skin effect, the RF only flows on that outer 0.01 millimeter of metal. So all you need is 0.01 millimeter thickness of copper, and you got a really good conductor. The rest can be anything. So you will see very commonly in low-loss lines, you'll see an aluminum or aluminium center conductor coated with copper, and that's why. As a matter of fact, we have tracer wire next door that is steel wire coated with copper. Makes great antenna wire because steel wire is strong as hell. It stretches almost zero. Very, very difficult to break. You worked with it. But yet it has that copper cladding, so for RF it's very efficient conductor. So they call it tracer wire, and they bury it with all the plastic water and gas service lines. So then you can buy it by what the heck was that spool?
It was 1,000 feet, wasn't it?
No, I think it's like 2,500 feet or
Whatever it
something.
was only $150 or
Yeah.
$200 sort of thing for the whole.
Well, they sell it by miles and stuff because everywhere that there's pipe being put down, especially plastic pipes, they run one of these wires with it. So it makes great antenna wire.
So on a multi-strand wire, does it all, like, does the skin effect go towards the outside diameter of the whole multi?
The outside diameter of the whole multi-strand, yeah. So really the only advantage to a multi-strand wire is its flexibility. Most times you run stranded wire, say in mobile installations, in vehicles, cars and trucks, where you need to bend cable around sharp corners and stuff. It's a good advantage there because it gives you more flexible cable.
So like the cable I bought from Alpha Radio was multi-strand
Yep.
in the middle. Is
Yep.
that better than solid core, or is it worse?
Technically it's a little bit worse because the outer diameter, the outer surface area is a little bit less. But once again, it's marginal. You're talking a short run of cable, maybe 10 or 15 feet long if you're in a vehicle. So in the grand scheme of things, it really makes a hill of beans difference, and the stranded stuff is just easier to work with because it's more flexible.
And it's more money.
Yeah. Well, if you buy the military grade stuff, it uses Teflon insulation because of the high temperature, and silver coated copper because silver is the best conductor. And you don't want to know how much that stuff costs. That's crazy expensive.
The government
Get
pays for it.
flex wire in different stages you can have. It could be just, when I was with Schlumberger, even the smallest wire was double rack. There was one rack going around in one direction and an inner core going the other way to make it even flexible.
Well,
Yeah.
have you ever heard of spaghetti wire?
Yeah, well, there's all kinds.
Can you use spaghetti wire as an antenna?
You can use anything as an antenna. The question is, how efficient is it going to be? So,
That's what I'm shooting at.
Yeah.
Is it efficient or not efficient?
they're-
Spaghetti wire is like multi-strand with ultra small strands,
Yeah.
right?
once again, it's the surface area of it all, and stranded wire typically has less surface area than solid, simply because of the gaps between the wires. So,
And flex is usually just for flexible applications. You usually find that with the finer wires, if you're going to have an antenna that's portable, so that you're going to take out in the field
Right,
and
and use
throw
it.
it over a tree.
Mhm.
And
That's exactly where I'm going. with
and
it.
that's basically what you want. You need that extra flexibility to be able to allow that to happen.
So it lasts a couple
Yeah.
more
That's-
years.
And yeah, that's right. And the other thing is you're going to coil it back up because you're only going to be there for a day or so
Mhm.
and bring it back and you're going to coil it up. And each time you coil and uncoil it, you're flexing it and it tends to,
copper has a tendency to work harden. Yeah, it's disgusting metal. It's a really good conductor, but it's not that great. When we talked about this, we talked about it as a lossless line. There's no such thing as lossless lines yet. So when we were doing that scenario, when we were talking about the SWR and we put 100 watts into that wire and we get 100 watts out, that never happens. There is always some loss. Every piece of wire has loss. Every piece of coax cable has loss. The loss is determined by the actual conductor, the ohmic resistance of the conductors. Now in heavy coaxial cable, that's pretty damn small. Loss is also determined in the connectors. Typically the connectors are much lossier than the cable itself. And that's why we like to, say use good quality connectors, buy expensive ones, don't buy Chinesium from MRO. And so on and so forth. But, there's loss every which way. And so if you can imagine with our SWR scenario, we're saying, okay, we got power coming this way and power coming back. Well, now the power going both ways is subject to loss. Because that 100 watts going one way is subject to line losses, and then that 50 watts reflected is subject to line losses. And let's say for some strange reason you are using very lossy cable and you put your SWR meter right at the arse end of your transmitter, which most people do, and you measure it and you go, oh, my SWR is 1.5 to 1, it's great. Well, if you've got high losses, the SWR at your antenna may be 3 or 4 to 1, but by the time that power is getting back to the SWR meter, it's been lost in the line and you don't really know what you're getting. So the only way to really measure antenna SWR is at the antenna connector, not at your transmitter connector. Because, eliminate losses, I guess is the thing.
The pole.
Yeah, it might be up the pole, yeah. Well, we ask somebody to shimmy up there with one of those, like my little meter there has a 2-meter transmitter built into it. So you can tune it to a frequency, put it in SWR transmit, and tune in on your 2-meter radio, and it plays a tone to you. And the high tone means high SWR, low tone means low SWR, and all that kind of stuff. Yeah, isn't that cool? What is the velocity factor of a transmission line? It's the velocity of the wave on the transmission line divided by the velocity of light. In other words, a ratio to the speed of light versus the actual velocity. And we said, what's the typical velocity for coaxial cable with polyethylene dielectric? 66, yeah. What kind of impedance does a quarter wavelength transmission line present to the source when the line is shorted at the far end?
Kind of impedance.
Yep. So if it's shorted at the far end, quarter wave means it's going to be an open circuit. Remember, it's going to flip that impedance around. So the answer they provide is a very high impedance. It's going to be close to an open circuit. What kind of impedance does the quarter wave transmission line present to the source of the line as open at the far end? So they ask the question both ways. Both questions are in the bank. So what's the velocity factor? What determines the velocity factor in the transmission line? And the answer is the type of dielectric, whether it's, we talked about polyethylene being really popular, Teflons, foam, all kinds of stuff. Moving through some other types of transmission lines.
Where does Teflon as an insulator, as a dielectric, fit in between? Does it have lots of air in it, or is it solid?
It's pretty solid. It's I think it's like about 72 or something.
Okay.
But the thing about Teflon is the temperature.
Right. Yeah.
So it can bear, like, what is it, 1,000 degrees C
Yeah.
or some damn thing?
Yeah, you got to work at it.
Yeah, it's very, very high temperature. So in places like furnaces and stacks and stuff where there's high temperature, you use Teflon graded stuff. Power loss and transmission. Okay, page 14-8, waveguides. I'm not going to draw pictures because they draw beautiful pictures there. Roughly at about, the rule of thumb is 1500 megahertz, 1.5 gigahertz and up. Coaxial cables just have too much loss. Even a short cable is very, very lossy at those high frequencies. So we go to traveling wave transmission lines, or better known as waveguides. And you can think of waveguide as a tube. It could be round, it could be oval or egg-shaped, or it could be rectangular. That you actually transmit the wave through the interior of it. The wave travels through the inside. So rather than having a center conductor and a shield like coax, You have a little tiny transmitting antenna and it transmits, and the electromagnetic wave propagates through the waveguide, completely enclosed, so it can't interfere with the outside, from point A to point B, and it's very much like plumbing. It can be round, it can be rectangular. Rectangular is by far the most popular. It can be elliptical, like egg-shaped waveguide, and it's hollow. There is no center conductor because you're actually launching the electromagnetic wave through it, and it propagates through the air inside there. Or in the case of very high power radar, they'll actually vacuum it out because the power is so high it'll arc in the air molecules. Okay. So waveguide is usually used at about 1500 megahertz and up, and they say that in about the second or third sentence there on page 14-8. And it's basically a hollow tube, like I say. It could be round, it could be oval. Most times it's rectangular in shape, kind of looks like a waveguide for 1500 megahertz looks just like a 2x4, you know, if you want to get a picture of it, the physical size of it. Okay. The cross section of the waveguide, whether it's round, we're talking would be the diameter if it's round, or the long section if it's oval, or in the case of rectangular waveguide, the wide part of the waveguide. Waveguide has to be at least a half wavelength at the frequency we're interested in. So you guys can do the math at 1500 megahertz. What's a half wavelength? It's, you know, I don't know, that long or something. Any frequency below that half wavelength is cut off, which effectively makes waveguide a high pass filter. Okay, it'll pass frequencies above that cross section half wave, but anything below is cut off. So waveguide, like I say, used above 1500 megahertz. It's very, very efficient, very low loss. So, you know, up in the microwave ranges and stuff, it's all waveguide. Many times, waveguide will use round or elliptical waveguide, and it looks just like hardline. If you take a look from the outside, it's got the same copper jacket with the same black covering on it and stuff, and without you actually looking at a cross section, you wouldn't realize that, oh, this isn't coax, it's just a hollow tube. Okay, so there's some over on the Rogers Tower here. They use some to go up to the old cell phone antennas, which are at 1600 meg, 1690, whatever that band is. Okay, waveguide is typically used at frequencies above 1500 megahertz. I said that. Waveguide is low radiation loss, low dielectric loss, and low copper losses, and that's all on page 14-8 and 14-9 somewhere. Because a waveguide is basically a sealed system, there is no radiation loss, no RF is escaping out of it until we want it to. So, what's the advantage of waveguide as a transmission line? Low loss. For rectangular waveguide to transfer energy, the cross-section needs to be at least a half wavelength. We said that. Waveguide has low loss at high frequencies, but high loss below the cutoff frequency. It acts as a high-pass filter. So, what precautions should you take before beginning repairs on a microwave feed horn or waveguide?
Wear tight clothing.
Yeah. On page 14-9, about 2/3 of the way down, there's a box there. And it says, if you're using waveguide, obviously you're working on high frequencies, extremely important for doing any work. The transmitter is disconnected from the system. Never look into the end of the waveguide, da-da-da-da-da, okay? So, it's just basic safety. And remember, microwaves at 2.6 gigahertz, like that oven up there, will heat things up very, very rapidly, the resonant frequency of a water molecule. And the ocular fluid in our eyes, everybody probably knows this, is the equivalent of an egg white. If you heat it up beyond its transition temperature, it goes white and it is irreversible. You are blind, period. There is no changing it, so you don't muck around when you're playing with this stuff. You know, the guy that invented the microwave oven, he had a chocolate bar in his pocket and he noticed it melted when he was working on it. It's amazing the guy had any eyesight left.
Well, it's no different than Madame Curie with
Yep.
the radiation,
Yeah.
right? I mean,
Okay.
So 1500 megahertz, that's,
1.5.
so that's 10 centimeter band? Is
That would be about 10 centimeters. So a half wavelength would be 5 centimeters,
5 centimeters? Okay.
which is 5 centimeters is what, 2 inches?
Yeah.
Yeah. Yeah, 2.5 centimeters per
But
inch.
that's
roughly.
nowhere on the scale of amateur wave.
No.
Because I'm looking at the rack
Yeah.
band plan.
Well, we have a band at 2.4, we have a band at 5 gig, and we have 10 gig, and then we got a couple up above 10 gig.
we've got the 1.2 gig, right?
Yep, yeah, we've got 1296, which that's low enough that we usually don't do waveguides. 2400 meg for very short runs. You could get away with coax. For anything long, you want waveguides. And even 5600 meg, I've seen a lot of people successfully use low loss coax. But once again, for short runs, like say under 20 feet long, something like that. Microstrip line, the top of page 14-10. Microstrip line is a form of printed transmission line. In other words, it's printed right onto a circuit board. They got a nice little picture of it on the page of, or the top of page 14-10, where they show using a printed circuit board or PCB to make transmission lines, and the microstrip line is actually traces on the board or used as transmission lines.
Raspberry Pi uses those on the little one.
Yep.
That's the
Almost all the Wi-Fi Bluetooth modules in laptops and cell phones and Raspberry Pis and all those modules use microstrip line antennas. Just because they're really cheap, because they're just part of the circuit board design, and you don't have to add any extra hardware or anything. You just use microstrip line. Microstrip line sucks in a lot of ways. Because it's only a single leg transmission line. It's not really balanced or unbalanced. It sucks, but it has virtually no shielding because it's out in the open. But hey, if it's an antenna radiating, well, you don't want shielding. But if you're coupling an RF stage in a device to another RF stage in a device, microstrip lines are almost never used. They actually use little tiny pieces of coax cable jumpering inside from one stage to another. You could use microstrip line, but because of no shielding, it's the okay. What is a printed circuit transmission line called? Microstrip line. Compared with coax cable, microstrip line has poor shielding. Okay, and to round out this whole area, as standing wave ratio rises, or in other words, as your SWR gets worse, so does the loss in the transmission line. This is caused by dielectric and conductor heat losses. Yeah, heat. Everything has loss. We have not invented the lossless transmission line yet. We're working on it, but it hasn't happened yet. So. Okay, so the next thing we're going to get into is antenna tuners and matching networks and T matches and gamma matches and all these other matches and L networks and pi networks and stuff like that. Does this sound like fun?
Okay.
Yeah. So, I'm going to go mostly by the book here. So, hang on here. I got to find the right page. So, we're going to jump ahead to page 14-18? Yes. 14-18. We're going to talk a whole bunch more about antennas a little bit later on, but on page 14-17, they start talking about a T match and a gamma match. And the problem with our transmitters and our coaxial feed lines that we love to live is that's called an unbalanced system. And what does unbalanced mean as opposed to balanced? Let's just take a pause and talk about that. What unbalanced means is if you take a voltmeter, in our case an RF voltmeter, and you measure the voltage on the center conductor, you're going to measure a voltage. If you measure voltage on the shield, you're going to measure effectively zero because the shield is grounded. But the two conductors, because there's two conductors happening, there's a center conductor and the shield, they are at different voltage potentials with respect to ground. So that is called unbalanced. In other words, they're at a different voltage with respect to ground. Okay? A balanced transmission line, if you took your voltmeter and you measured one wire and the other wire, and that's things like twin line, okay, they will measure the same voltage with respect to ground. The voltage may not be in phase. We don't care about that. We're just looking at the overall amplitude. So a balanced line means both conductors are at the same potential with respect to ground. They may be 180 degrees out of phase, but that's irrelevant. Where an unbalanced is they're at different potentials with respect to ground. All of our transmitters and our coaxial cables are all unbalanced. The shield is at ground potential, the center conductor has got all that RF energy on it. Unfortunately, there isn't an antenna in the world made that is unbalanced. All antennas want to see balanced transmission line feeds. So we have to come up with a way to fool our antennas into thinking they're being fed by a balanced source. So we need to take this coax center conductor that's got all the RF energy and shield which has got ground on it, and we need to somehow connect that in the antenna and make the antenna think that we are connecting a center conductor and the ground, but the ground's going to have the opposite, that equal potential on it. So to do that is called a balanced to unbalanced converter, or the other way around is unbalanced to balanced converter. But the one that we use mostly is called a balanced to unbalanced. Okay, so we need to take this coax cable, which is unbalanced, we need to balance it to put it out to an antenna. And there's a number of ways to do that. And we start with something called the T match and the gamma match. Now the T match is actually specifically meant for balanced line, like ladder line, going to an antenna. Antennas, which we'll talk about shortly. Anybody know what the characteristic impedance of a dipole is? If you go string up a half-wave dipole wire antenna, what's the impedance?
Around 400.
No.
50.
No. Just to piss us all off, it's 72 ohms. No, that's in free space. So if you can hang it up at least 10 wavelengths away from everything, it's 72 ohms. You can do that quite easily on the high UHF frequencies, but try and do that on 160 meters. 10 wavelengths away, yeah, it ain't gonna happen, right? But a dipole antenna, which every antenna in the world is based on, is 72 ohms. So, throw that one in your head. Here we're using 50 ohm transmission lines. So, I mean, right there, we have a 1.25 to 1 SWR. Or worse. Just because of that. So we need some way to match these impedances, because when they match, everything's happy. So the T match is meant for like ladder line or parallel conductor line. And there's a nice little picture of it on the very top of page 14-18, figure 14-11. And the ladder line is quite high impedance. Ladder line is about, you said 400 ohms, depending, 300 to 450 ohms, depending on how big the windows in the ladder are, or if there is any. And the antenna is 72 ohms, so we need to match, say, 300 to 400 down to 72. So the T match provides a high impedance line down to the low impedance antenna match, and it's basically just two capacitors. Variable capacitors. The gamma match is the one that we're much more used to seeing is for coax lines. And this is where we simply take the ground braid of the coax and hook it directly to one element of our dipole. and we take the center conductor of our coax and we put it through a capacitor and hook it to the other element of the dipole. Okay, and by tweaking that capacitor, we can hopefully match the impedance of our antenna, which is roughly 72 ohms, to our 50 ohm line, and be happy. But the biggest problem with the gamma match is we have now taken an unbalanced line and we've hooked it up to a balanced antenna, and RF being what it is gets back into the shield of the coax and comes back all the way down into your shack, and when you touch your microphone you get a zap because there's RF coming back down. So we need to somehow stop that RF from coming back down the outer conductor of our coaxial cable. Okay, so those two matches, the T match was for balanced line, the gamma match is that matches the 50 ohm impedance from, in the case of coax, or the 300 or 400 ohm impedance in the case parallel to the antenna, but it does nothing to stop the RF coming back down because we're driving a balanced system of an unbalanced line. So we use something called a balun, and the balun is supposed to help us eliminate that RF returning back down. Okay, so there's a number of ways to do that. There is something that on the exams they call a stub match, but the proper name for it is a shorted quarter wave section, and that's on page 14-19. Near the top of the page they say shorted quarter wave section. You can write stub match right beside that. Stub is in a piece of stubby coax. And you can see what they're doing there in the little picture in 14-13, where they're taking the shield of the coax and hooking it directly up to one leg of the antenna, and they're taking the center conductor of the coax and hooking it up to the other leg of our dipole antenna. But then they've got that weird stub, that quarter wave section of coax in there, kind of hog-tied in there. And in the book, in that first paragraph under that section there, I think it's the second sentence, says equal and opposite currents flow on the surfaces of the coax cable feeder and the quarter wave coax stub section. So if they're equal but opposite, that means they cancel out. So going back down to the transmitter, you have your lovely balanced line and your RF's not going back that way, but the antenna is acting balanced. Works really good, but it only works really good at that one narrow band of frequencies of what that quarter wave is cut to.
So you would have to build that for every frequency you want to run.
Yeah, pain in the ass. But if all you did was 20 meter CW contesting on a little sliver of the 20 meter band, you can very easily make an antenna that way, and as long as you don't tune outside that range of the band, it'll work fine for you. So everything's a compromise. It's a simple thing to make, but it's a compromise. It's a very compromisey thing. So
This polka dot line here, that's a different kind of wire or something, or?
it's the braid, the one with the dots on it. That's the coax. That's the outer shield or the braid. That's just the way they're showing they're differentiating the braid from the center conductor.
Okay.
If that makes any sense. So. Okay. So the ultimate thing that we like to do is, instead of pissing around with quarter wave pieces of coax that you have to cut for all the different frequencies, we like to use antenna tuners, don't we? You know, almost every modern HF radio that you go and buy off the shelf now, except for the very, very basic ones, come with an ATU, an automatic antenna tuner, built into an automatic tuning unit. And we're going to talk about how they work. Okay. We're going to flip over to page 14-22. And what we're going to do is we're going to put a magic tuning network in between our transmitter and our antenna that is basically going to fool our transmitter into thinking there's a perfect 50 ohm load out there. Okay. And as we know, when we put up an antenna, there's always stray capacitances and stray inductances and stuff that we can not really avoid. So we can tune it out. And there's various kinds of antenna tuner they talk about there on the page. One is called a transformer antenna tuner, and a transformer is exactly like when we talked about power supplies with a primary and a secondary winding and all that kind of stuff. Transformers are good for pretty much all matching ranges. If you have to match, remember your transmitter is 50 ohms, but if your antenna is say 300 ohms, transformers will match to that. It'll match to a 72 ohm dipole, no problem, no problem. The problem with transformers is they're expensive, they're heavy, they really get expensive and really heavy when you get the high power handling ones. And because of that, they're reasonably uncommon. You don't see a lot of transformer ATUs around. But they do match the whole wide range of things. And of course, you need one transformer for every impedance match you need to match. So if you got 3 different antennas, you got to go buy 3 different transformers. Okay, they're fixed ratio because remember transformers have a primary winds and secondary winds. Well, yeah, all that stuff. So the next thing to do is talk about the Pi network, and we're going to be at the bottom of page 14-22, and the Pi network is shown in a nice little diagram on the top of page 1423. And the reason they call it a Pi network is you got the 2 variable capacitors and a coil, and they look like the symbol for pi. Capacitor, coil across the top, capacitor going down. They look like a pi, so that's where it came from. The Pi network gives the widest range of impedance transformation of any design. So if you want to be able to tune a wet noodle on 160 meters, you need a Pi network. Okay. What else do we need to say about a Pi network? Pi antenna is good for all impedance ranges, 1 inductor and 2 capacitors, or it could be 2 inductors and 1 capacitor, but they're in the Pi configuration. Has the widest transformation ratio. Okay, good. Moving on to the L network, which is on page 14-23. L network is got a reasonably narrow tuning range, and it's good for high impedance antennas. So things like these folded dipole loops that are 300 ohms, an L network works for that quite well. But it only works for a narrow range. So we're not talking of tuning a wet noodle on 160 meters. It's not going to happen with an L network. And L network, vertical ground plane antennas, by the way, their impedances are quite low. They're in the order of 70 ohms or something. L network won't tune down that low, so it's not suitable for a ground plane antenna. They say that there. Okay. What else am I supposed to say here? Oh, I missed that one. Oh, these guys are going to be pissed. Oh, okay. Oh, there it is. Thought I missed it, but I didn't miss it. Okay. Sorry, just skipping back to page 14-22, just above the Pi network, there's a couple of sentences. It says, the following circuits transform one impedance to another by canceling out the reactive part of an impedance with reactance of opposite value and changing the resistive part of the impedance. Got that? Everybody seen that sentence? Mm-hmm. So the question is, how does a network transform one impedance to the other? That's the question. And the answer is it cancels the reactive part of an impedance and changes the resistive part. Now, that's the question and the answer from the question bank. I just going to back up and talk about that a little bit more. All of these circuits, whether it's a pi or an L or a combination of two, a pi L and T's and all that kind of stuff, all they're doing is we have an antenna system out there. That antenna system has some inductance, some capacitance, and some resistance. Our transmitter wants to see no capacitance, no inductance, and 50 ohms of resistance. That's what we want to see. Okay? So all of these networks give you the capability of taking the capacitance and inductance that is out there on your antenna and nulling them out. And how do you null them out? Well, if you've got so many ohms of inductance, you add so many ohms of capacitance to cancel it out. And vice versa. If you have so many ohms of capacitance reactive, you add the equivalent of inductor to cancel it out. And then what's left is pure R for resistance, and you need to either add or subtract resistance to bring it to 50 ohms, and your transmitter is happy. So all that I just said is what they said in that sentence. Say canceling the reactive part of an impedance. So the reactive part is either the inductance or the capacitance, or in some cases both. And then changing the resistive part, bringing the resistive up or down to 50 ohms. So, which three types of networks are most commonly used to match an RF power amplifier to a transmission line? Well, the three types of networks that are most commonly used are L, pi, and pi-L. And the advantage of the pi-L network is it's a pi. First off, we talked about the pi, saying it has the widest transformation range it could do in a wet noodle. We said the L isn't that great, it's narrow, but if you take a pi and follow it by an L, you get the best of both worlds. You get this thing that can tune a wet noodle on 160 meters, and the L network, if you look at the L network, it happens to look just like a low-pass filter, doesn't it? If you look at on page 14-23 and figure 14-22, they have the four little schematic diagrams of an L network. Well, if you look at schematic diagram A of the L network, that's a low-pass filter, right? Just think about it. What's going to happen at DC? DC is going to squirt right through there. But at very, very high frequencies, the RF is going to shunt through that capacitor to ground. So now you have a thing that can tune a really wide range and a low-pass filter, which helps you get rid of the harmonics and the other noise that your station may be generating, and that's the best of one world. And all of these MFJ Versatuners with buttons and knobs and stuff are usually pi-L networks. Okay. Okay, so, oh, we got time. We're doing good. Okay, everybody relaxed? I know I am.
Video.
I'm gonna close these blinds here just to make it a little darker so everybody can sleep.
Did you bring some?
Oh, you know, that would be so good right now.
Yeah, quick, get the popcorn.
How dare you mention it and not having even had
If the instructor hadn't had implied that he was going to show a video, I might have been tempted to bring popcorn.
Okay, skip the dishes, popcorn.
How quickly can they get here?
Okay, that doesn't seem to be working.
Oh, bummer.
There it goes. That was the center.
Ah, that's what's happening.
There we go. Move it over to where it's supposed to be.
I thought it said an official Royal Canadian Air Force for a second.
Yeah, kind of.
Popcorn, we have cookies.
Not the same.
Yeah, grab a cookie, grab yourself a coffee, a water, whatever.
Alright, then I'll grab
This
some.
is about,
12 minutes.
it's 12 minutes, just over 12 minutes long, so it's not too long. So I'm gonna play this and then we'll stop and I'll talk about a few things we need to talk about. And there's two more, there's a total of 3 videos we're talking here. And they're all about the same length. I didn't have external speakers, but I cranked my volume on my laptop up to 100%, so hopefully you can hear it. If we can't hear it, well, We'll figure something out. Actually, I can probably pipe the audio up to that, but
Does that have a speaker in it?
that has audio too, yeah. As a matter of fact, which audio am I connected to?
Skip the dishes, popcorn, no match.
Dang it!
Oh, I am connected to the, okay, I'm connected to the audio up there. So the audio should be coming from up there.
Nice.
Okay, so let's try. Everybody ready?
Yeah.
The shape and size of an antenna is a function of its purpose. But whatever its physical form, it is designed to transmit and receive electromagnetic waves. Let us first consider a hypothetical antenna, the point source. From such a source, energy radiates outwards in all directions.
Pretty good graphics, eh?
Let us examine this process more closely. The radiated energy can be represented by a traveling waveform of this shape. The waveform normally follows a sine curve. We will consider one complete cycle of the wave. It is defined as one wavelength. We can relate the wavelength of the radiation to the antenna which produced it. An antenna which accommodates half a wavelength is the simple dipole. If we feed a signal to this antenna, an electron flow will be set up within it. The electron flow first produces a maximum concentration in this direction, reverses, then produces a maximum in the opposite direction. Flow reverses, maximum. This cycle repeats itself at the signal frequency. This electron flow creates a fluctuating magnetic field. Let us relate the direction of this field to the electron flow. As the electron flow reverses, the magnetic field is at a maximum, and the lines of force are in this direction. When the flow stops, the lines of force collapse. As the flow reverses, the field again reaches a maximum. The lines of force are now in the opposite direction. The magnetic field thus reverses its direction at each half cycle of the signal frequency. This is known as the H field. The strength of this field is proportional to the amplitude of the current standing wave. This current standing wave is 90 degrees out of phase with the voltage standing wave. At this instant, the antenna has a positive voltage at this end and a negative voltage at this end. When the voltage builds in the opposite direction, the polarity reverses. This changing polarity produces an electric field in phase with it. When the voltage is of this polarity, the field is in this direction. When the polarity reverses, the field builds to a maximum in the opposite direction. This is known as the E field. The E and the H fields thus build and collapse 90 degrees out of phase with each other and constitute the antenna's immediate field. This immediate field produces the radiating wave pattern. From the antenna, we can visualize the radiation as a series of grids propagating outwards. The vertical lines are the H component, and the horizontal lines the E component. Notice that the lines are at right angles to each other, that is, in space quadrature. Vectorially, these lines represent the peaks of the radiating waves. Notice that their direction reverses at the next half cycle. Since the peaks of these two waves occur simultaneously, they are in time phase. The traveling waves are therefore said to be in time phase and space quadrature. The polarity of an antenna is determined by the plane of the E field. To obtain a maximum signal, both the transmitting and receiving antennas must be in the plane of the E field. The direction in which the E and the H wave pattern propagates is determined by a simple rule. To apply this rule, we use any two vectors. Imagine a corkscrew action. If we turn from the E vector to the H vector through the shortest distance, the screw has advanced in the direction of propagation. This is known as Poynting's vector rule. In the next half cycle, the E and H vectors reverse. Applying Poynting's rule again, we see that the direction of propagation is unchanged. Although we have considered only peak vectors, any vector pair would give the same direction of propagation. Let us now consider what happens when the wave strikes a reflecting surface. We will consider only one pair of the peak vectors. As before, Poynting's rule gives the direction of propagation. On reaching the reflector, the E field is reversed, but the direction of the H field is unchanged. By Poynting's rule, the direction vector is therefore reversed. The same process occurs for each successive pair of vectors. The direction of propagation thus reverses when the wave strikes a plane surface. Let us now see how we record the intensity of the energy radiating from an antenna. First, we sample the signal strength at various points. Such a record is geographical, and we can join the points of equal intensity to obtain contour lines. It is often more useful to know the shape of the field radiated by the antenna. To achieve this, we obtain field strengths at a fixed radius from the antenna. We now use a vectorial presentation to give each reading a magnitude and direction. To plot this, we use a scale of circles. Along this line, the field strength on the selected radius is 3. So we cut the line at the circle representing strength 3. Along this line, the field strength is 4. So it is cut at the strength 4 circle. By continuing the plot in this way, we obtain a series of vectors. These vectors represent the strength and direction of the field. Joining the tips of the vectors, we obtain the antenna's polar diagram. The complete polar diagram is three-dimensional, and it enables us to visualize an antenna's radiating characteristics. Let us now review the basic elements of antenna propagation. A half-wave dipole, excited by a signal, will have an electron flow set up within it. This movement of electrons creates two fields. These fields, building and collapsing in time and space quadrature, form the antenna's immediate field. This immediate field produces the radiating wave pattern. We can represent this radiation by vectors. Associated with these vectors is the traveling wave pattern. The traveling wave is in time phase and space quadrature. The fundamental characteristics of this traveling wave and the means by which it was produced are the same for any antenna system.
Theory hasn't changed since 1959, so anyways, the important things to remember there are, what am I supposed to remember?
E field, H field.
E field and H field. Polarization is always determined using the
E field.
E field, right on. And one thing he didn't talk about was circular polarization, but I mentioned it earlier today, is where the E field, well, and H field are kind of going in a corkscrew arrangement. So, in other words, the E field is rotating. It's not just horizontal, it's not just vertical, it's rotating round and round in corkscrew fashion, kind of.
The antenna is rotating as well.
So,
What was the immediate field? I kind of lost that part.
Nowadays they call that the near field of the antenna. And the near field is considered to be within, 10 wavelengths of the antenna. You actually can detect those things, but once the wave is launched out into the ether, it becomes the quadrature electromagnetic wave that we're all so friendly with. But when you're at the antenna, or very close to the antenna, the magnetic field and electric fields are still there, and they're still individual fields that you can see and measure and experience. But once you get about 10 wavelengths away, they're combined into that propagation, the sky wave, so to speak, and they're one and the same.
So you literally, to map out and vector this field, you literally go out in the field with some kind of
Signal strength meter, like a spectrum analyzer,
and you measure
and
plot
you measure it, and you say, I'm here and it's this much, I'm over there, it's this much, I'm over there, this much, and you plot it out. Yep.
So where do the plots come from on
online when you look at a repeater, it says it covers, and it's not.
That's done with a path prediction software. So all kinds of information is put in as to where the repeater is located for geographic area, obviously, how high the antenna is above the ground, how much power they're putting out, what frequency they're operating on. And what that is it just looks at the terrain of the earth, the ups and downs, the peaks and valleys and whatnot, and looks at the height of the antenna and just draws vectors. It's just mathematical. They draw vectors from there going, okay, well, that antenna is going to hit the horizon, 12 kilometers away in this direction, but 20 kilometers away in that direction. So that means it's got more range over there than it does this way, and so on and so forth. And the computer prediction models are actually really good. And like anything, the more information you put into them, the more accurate they are. So the more accurate you can be about your antenna gain and patterns and power outputs, and the actually terrain elevation stuff is really important. So which one do I have here?
What materials reflect radio waves better than others, for example?
Anything conductive reflects a radio wave. So any piece of metal. And got to remember that a lot of the tall office buildings downtown are all glass. What's in that glass? Lead.
So if you're inside an Airstream trailer, you're not going to get any radio.
Yeah, you're pretty much in a sealed cavity. Yep.
That's right. I have that problem at home. I've got an aluminum sided house. My Wi-Fi doesn't go up. I go out on my deck and I can barely get my Wi-Fi because of the aluminum side. The same with a lot of these glass buildings are high E glass to protect this from the sun.
Yeah.
Well, it's the same problem getting the radiation out. Sorry.
What about stucco chicken wire? Is that
Same thing.
Well, I don't know if any of you mess with handhelds from inside your vehicles, but on 2 meters, you'll notice you have a hell of a time hitting the repeater from inside your vehicle. But if you flip to 70 centimeters,
that's where you got to go like this.
at 70 centimeters, you'll find it works a hell of a lot better. And that's because the openings, i.e. the windshield and the rear window and the side windows at 70 centimeters are now big enough that it lets the waves through. At 2 meters, it's basically just a sealed cavity. It's just like that microwave oven. You can look through the holes in the door and see what's cooking. It's because the holes are small enough that the wavelength of the radio waves can't get through it. If the holes were bigger, you wouldn't want to look at it.
Because I know, well, this last net, there's a guy complaining, I think he lives over northwest there, and he says, how come I can't get my power's going down? Well, all the tanks and all the new buildings going up, he's right direct line. He says, I'm down 50%.
Mm-hmm.
Mitch was saying, well, we'll check into it, but he said there's a lot of steel between you and there now.
Yep.
Absolutely.
Yep. Any conductive thing will reflect, so. And of course then it depends on the wavelength too, so.
But wood and stuff like that, no problem.
Oh, how many nails are in the wood?
Nowadays a lot, so you hear those guys up there.
So, I mean, it's, yeah. Like kiln dried wood has got very little moisture in it, so it's pretty much transparent to most RF. But then you put nails in it and you put those metal braces in it and, joist hangers and stuff. There's metal all over the place that you don't really think about. So.
And that just makes spurs that interfere, or does that totally eliminate the wave?
Well, it can reflect the wave, or it can reflect portions of it, or stuff like that. So fun. So how long is this one? I think this one's probably about the same. Yeah, 12 minutes and 4 seconds. So that first one, as you're seeing, was more or less just propagation, and the E field and the H field and that kind of stuff. So the next two, which is more antennas, and that's what we're going to hit hard here, is antenna theory. So this first one talks about antennas and how they make them directional, and then the second video on antennas is to increase the bandwidth of an antenna, because the perfect dipole only resonates on one frequency, And us hams, we don't like operating on one frequency. We like operating on a band or several bands, plural, of frequencies. So the first one is talking about antennas and directivity. In other words, how to make them directional and give them gain. And the second one is how to increase the bandwidth of an antenna system or communication system in general. And once again, they're lovely things. And if anybody wants these movies, they're 125 meg, give or take, each. And if you got a USB stick, you can even bring a USB stick tomorrow if you want. You can happily take away a copy of these things.
I'll do that.
Yeah, so.
You don't like filming?
Well, they're not the greatest quality, but then you don't really need great quality to see. As long as you can hear them and get a gist of what's going on, they're fine. So, okay, let's.
I believe they're on YouTube.
Oh, I'm sure you can find them somewhere. I collected them. I threw them on my hard drive years ago, and I just kept them so I don't have to go hunting for them all the time.
This is a simple half-wave dipole. Viewed from above, it looks like this. And we can represent its radiation pattern as a series of expanding circles. It is often desirable to concentrate this radiated energy into specific areas. In other words, we wish to make the antenna more directive. To see how this is achieved, let us return to the omnidirectional pattern. Here, red represents the positive peaks and blue the negative peaks. The distance between two peaks of opposite polarity is 1/2 a wavelength. We will introduce a second dipole spaced 1/2 a wavelength from the first. If we feed both dipoles 180 degrees out of phase, we obtain this radiation pattern. In the plane broadside to the antennas, the waves are 180 degrees out of phase with each other. The waves propagating in this direction thus cancel each other out. Useful propagation has thus been achieved in two directions, by feeding the dipoles 180 degrees out of phase. If we feed the dipoles in phase, we obtain this radiation pattern. This time, waves in the plane of the antennas are out of phase. The waves propagating in this direction will thus cancel each other out. By feeding the dipoles in phase, we again achieve useful propagation in two directions. By adding extra dipoles 1/2 a wavelength apart, we can concentrate the radiated energy still further. Let's now review how bidirectivity is achieved. A single dipole with its omnidirectional radiation pattern produces a donut-shaped polar diagram. By adding a second dipole, half a wavelength from the first, we have altered this polar diagram to produce two lobes. By increasing the number of dipoles, we have sharpened these lobes. To aid this presentation, the antenna size in relation to the polar diagram is greatly exaggerated. These bidirectional qualities are thus produced by spacing dipoles half a wavelength from each other and feeding them in phase or out of phase. Three practical examples of this type of array are the broadside, the collinear array, and the end-fire array. All these antennas concentrate the radiated energy in two directions. In some cases, however, it is desirable to concentrate the radiated energy in one direction. To see how unidirectivity can be achieved, let us return to the simple dipole. A quarter of a wavelength from it, we add an undriven element which acts as a reflector. Again, we can view the elements from above. A wave leaving the antenna reaches the reflector a quarter of a wavelength later. Due to inductance, a wave of opposite polarity is produced. When it reaches the antenna a quarter of a wavelength later, it is in phase with the wave then being created. The resulting radiation pattern looks like this. Notice that in this direction, the waves cancel each other out, while in this direction, they reinforce each other. Unidirectional radiation is thus achieved by adding a reflector a quarter of a wavelength from the dipole. And the polar diagram shows how the radiated energy is now concentrated into one lobe. Similar lobes can be produced by adding suitable reflectors to our three typical antennas. Here is the broadside, the collinear, and the end fire. The upper VHF region sets the practical limit to this type of array. It is more convenient to control the radiated energy and narrow the beam width in the microwave region. Because the microwave region is close to that of visible light, we can now use optical principles to solve our radiation problem. Let's briefly review a simple optical principle. Here's a plane surface. Light, striking it at this angle, will be reflected at an equal angle. If we arrange a number of such reflecting elements so that the reflected rays emerge parallel to each other, our reflector becomes a parabola. All path lengths from the focal point will be equal. Energy will thus radiate in a plane of uniform polarity and intensity. The practical parabolic reflector is three-dimensional. And this type of antenna concentrates the radiated energy into a single lobe. It thus provides maximum directivity for transmission with good capture area for reception. Other antennas can be derived from the basic parabola, such as the parabolic cylinder, the orange peel paraboloid, and the cosecant squared antenna. All these antennas are made directive by the application of simple principles. From the simple dipole with its omnidirectional radiation pattern, which produces a donut-shaped polar diagram, we can arrange the feeding and relationship of additional elements to change the radiation pattern. And produce a bidirectional polar diagram. We can further concentrate energy by the use of reflectors. And a unidirectional polar diagram is produced. The application of these simple principles facilitates the design of antennas which concentrate energy and increase receptivity in the desired direction.
One more and then we'll take a break.
Close that.
Where is there it is.
Broadband antennas have been developed to serve many different functions. Let's consider some of the requirements that must be met in the field of communications. The sounds we hear are contained within a frequency spectrum which is approximately 10,000 cycles wide. The amount of intelligence which we can convey is therefore related to the width of the spectrum. This simple 500 cycle tone can be represented mathematically by a sine wave. To this fundamental, we will now add the second harmonic. The change of sound is caused by the modification of the wave shape. A further change in the sound is caused by the addition of the third harmonic. The waveform has again been changed. Each increase in spectrum width increases the quality or intelligence conveyed by the sound. If we play a 500 cycle note on a saxophone, the harmonics create a distinctive wave shape. If the same note is played on a flute, we obtain a different harmonic pattern. Again, the wave shape shows that we must pass additional frequencies to retain musical quality. It is the harmonics which identify different musical notes. The human voice, which can be likened to a musical instrument, is best depicted on the larger spectrum.
1, 2, 3, 2, 1.
On an average, the frequency range is about 8,000 cycles. The associated wave shape looks like this.
1, 2, 3, 2, 1.
By filtering out inessential harmonics, we can reduce this range to 3,000 cycles.
1, 2, 3, 2, 1, 2, 3.
Since the intelligence has been retained, we have produced a voice channel. To understand how this information is transmitted, let's return to our 500 cycle waveform. To facilitate transmission, we frequency modulate a carrier wave. Here's what happens. When the waveform is positive, the carrier bunches together. This process produces a sum frequency. When the waveform swings negative, the carrier is expanded. This process produces a difference frequency. If we change the waveform to that of our speech channel, the resulting modulation will be more complex.
1, 2, 3, 2, 1.
Let's assume that our carrier has a frequency of 30 megacycles. The modulation process produces sum and difference frequencies.
1, 2, 3, 2, 1, 2.
This block represents one channel of information. In practice, it is desirable to widen this range so as to transmit and receive a number of channels of information. This requirement is not achieved with the simple dipole. This antenna has a high efficiency at a spot frequency. That is to say, a high Q. To increase its bandwidth, we must lower its Q. This process is known as broadbanding. Let us see how it is achieved. In the VHF region, we can fold the dipole or change the rods to current sheets. In the UHF region, the upper element can be replaced by a capacity hat and the lower element by a cone. This antenna has directivity and broadbanding, but has less gain than a simple dipole. The squirrel cage antenna overcomes this limitation. It is usually mounted as a vertical array. This antenna concentrates power and provides high gain as well as broadbanding. Let's return to our single voice channel and consider a further example of the need for broadbanding. It is often desirable to transmit many voice channels. The electronic compounding of all these voice channels produces a baseband signal which may be many kilocycles wide. To transmit this baseband, we might use a carrier of 600 megacycles. Again, sum and difference frequencies are obtained. Each block represents a carrier being modulated by many voice channels. Broadbanding in this region enables us to handle a number of carrier frequencies. As before, we must lower the antenna's Q to achieve this broadband requirement. Broadbanding in the microwave region is easier to achieve. Because of the smaller wavelength, our dipole is physically smaller. And we can lower its Q by increasing its rod diameter. In this form, the antenna is very inefficient because it affords a very small capture area for reception. By adding a reflector, we can restore our high-gain broadband requirement. Some installations use flared horn and lens systems. Others use large, high-gain dishes. All these antennas have a greater bandwidth and higher gain than those used in older HF systems. Broadbanding thus permits greatly improved methods of communication with increased flexibility. The line of sight system gives high traffic capacity over short distances. Range can be greatly increased with the tropospheric scatter system. In this system, the beam is directed at the horizon. Its energy is then re-radiated by the millions of particles in the atmosphere. This re-radiated energy is picked up by high-gain dishes. Even greater range is possible with the ionospheric scatter system. A powerful beam is directed at the ionosphere. Reflection occurs, and the reflected energy is then picked up in the target area. To achieve these greater ranges, we must accept some loss of traffic capacity, but with communication systems like this, we can span the globe. Even the faint radio signals from outer space can be picked up with super high-gain reception equipment. While the tracking of satellites is achieved with great accuracy. Antenna design and performance will be a vital element in the development of equipment for the space age.
I thought you were right into it.
Let's take a 10-minute break, 3:15.
funny. My dad was using intelligence in that definition to explain things to my mother. And my mother studies psychology, which has a very different use of the word intelligence.
The term intelligence is a poor one, especially around here.